Take one of each. The definite integral. Neil, send him up. Recall that one method of determining the area under curve y equals f of x from a to b is to, up front, well, fine, whatever. Is to use the limit of the, so this is actually, you're going to be tested on this on Monday, right?
What?
Yeah. Yeah?
Really?
What? Yeah? Okay. The formula is on the formula sheet, right? That's the area under a curve, right? Limit is also very useful in determining other quantities such as volumes, lengths of curves, areas of surfaces, and physical quantities such as work and force. We therefore give it a special name, the definite integral, and this special symbol, which is an elongated S and is attributed to Leibniz. In the great, was it Leibniz or Newton who developed the calculus debate? All right, so here we go. Let f be a continuous function defined on the interval, closed interval ab. The definite integral of f from a to b is written as, so you've got the integral from a to b, f of x dx, is equal to the limit as n approaches infinity, the sum of I equals 1 to n of f of x sub I delta x, where delta x is b minus a over n, and x sub I is a plus I delta x. This symbol is called the integral. The integral. In the notation, the integral from a to b of f of x dx, f of x is called the integrand. A is called the, take a wild guess, the blank limit. Yeah, lower. And then B must therefore be called the higher. Yeah, or upper. Okay, I'm not asking any more questions. Okay, so we've got a lower limit and an upper limit. The symbol, the integral from a to b of f of x dx, should be regarded as a single symbol. Okay. None of the pieces can be taken away, and the significance of dx will be explained later. The process of calculating an integral is called integration. For the special case where f of x is greater than or equal to 0, right, where the thing lies above the x-axis, then the integral from a to b of f of x dx is equal to the area under the curve, y equals f of x from a to b. Okay, so we've kind of been working with that, right? All right, good, first page. Use the definition of the definite integral to evaluate the integral from 0 to 5 of 3x minus x squared dx. Okay, so we've done this, if you remember the botched up one, so we'll do this one cleanly. Okay, and you may, so start off with the definition, right? So 0 to 5 of 3x minus x squared dx is equal to the limit as n approaches infinity, the sum of I equals 1 to n, f of x sub I delta x, right? Which I think is on your formula sheet, is it not? I don't have a formula sheet handy. Formula sheet. Yes. Yes, it is. Okay. So that's all defined on your formula sheet, which could come in quite handy on Monday, right? Where, and then it goes on to say what delta x is, right? So what's delta x for us? Well, here's the formula, which will be on your formula sheet on Monday. What's B? 5. What's A? What's N? N. So delta x is 5 over n, right? And what is x sub I? So again, as on the formula sheet, x sub I is defined as, of course I hole punched right through it.
A plus I.
Yeah, a plus I delta x. Which is, so a plus I delta x, which is 0 plus, well, 5I over n, or just 5I over n, right? Okay, so having established that, we can now just kind of fill it in and work it down, as you will on Monday. Dropping a small hint. All right, so come on, this is old stuff, right? We're just doing it an old school way. All right, so what do we got? The limit as n approaches infinity. So I'm moving this over here because I'm going to need space, like 2 columns. Okay, so you might want to do the same because it's going to take up some space. Sum I equals 1 to n. Let's do the delta x first. So 5 over n, whoops, and f of x sub I, which we have figured out is 0 plus 5i. So let's write the whole thing in there. Just in case a isn't 0, right? So we actually have to put a number in there. Like, if it was from 1 to 5, this would be 1 plus 5i to the n. Okay, so now we can keep going. So the limit as n approaches infinity. The sum of I equals 1 to n, 5 over n. All right, so what's f of 0 plus 5i? Right, so what we do is we look at the definition, right? F of x is 3x minus x squared. So I'm going to take 3 times this, which is just going to be 15i over n. Okay, 0, we don't care about it. So 15i over n. Or let's do this. So 3 times 5i over n. More details. Minus 5i over n squared. Okay, because the 0, right? I mean, so life is nice if it's a 0. If there's a number in there, this would be 3 times, 2 plus 5i over n, and this would be 2 plus 5i over n squared. All right, so we just keep working. Limit n approaches infinity. Now, in the review sheet, which I told you about, right, which is in Schoology, so there's the review, right, you got the text. So there's a review in the area in antiderivatives. There's a review sheet with worked out solutions. And Ms. Tong does it a slightly different way. You'll kind of figure it out when you see it. Okay, it's the same, only different. Okay, so what do we got? 5 over n, and we've got 15i over n minus 25i squared over n squared. All right, so just make sure you're squaring things correctly, right? That you square the top and the bottom. Limit sum. So we've got 75i over n. So 5 times 15 is 75i. N times n is n squared. Minus 125 I squared over n cubed. Now at this point we could say, well, wait, 75 and 25 are both divisible by 25, right? So we can pull a 25 out, right? So we can pull that 25 out. We could pull it out front. So it becomes 25 times the limit as n approaches infinity of the sum of I equals 1 to n of 3i over n squared minus 5i squared over n cubed. Right, and now we can do the sum. So now we go to the next part. Right beside this formula on the formula sheet are the formulas for the sum of what do we got? The sum of I equals 1 to n of I squared, n of I cubed, right? So we get 25 times the limit as n approaches infinity. And now we're going to do the summing up. So we get 3. Okay, so the I is replaced by n times n plus 1 over 2. And then there's the n squared, right? Okay, so that's off that formula sheet, right? The sum of I equals 1 to n of I is n times n plus 1 over 2. Minus 5. Okay, now we're doing I squared, and the sum of I squared is n times n plus 1 times 2n plus 1 over 6. And then we've got the n cubed. And continuing on, we now are going to simplify, right?
So from the 3i over n squared to the next step, that's in the formula sheet? Like you can
Yep.
figure that out too.
Yep. So what you see here, n plus 1 over 2, that's on the formula sheet, right? So the I, since you're doing a sum, right? So we're removing the summation. We're doing the sum, and the sum of I equals 1 to n of I is n times n plus 1 over 2, and then that's being multiplied by 3 over n squared, right?
Yeah.
And the sum of I squared is n times n plus 1 times 2n plus 1 over 6, and that's being multiplied by 5 over n cubed. Okay? So now, here we go. There should probably be like equal signs here, right? Okay, so we got the 25. We've got the limit as n approaches infinity. So what we're going to do is we're going to split the n squared up into n times n, and we're going to divide this n by one of those, and we're going to divide this term by the other one of those, okay? So that's kind of the key there, right? So we've got 3 times 1, right? N divided by n is 1, times 1 plus 1 over n over 2. So what we've done, we took the n squared, we're thinking of it as n times n, and I'm dividing this n by one of them, so n divided by n is 1. I'm dividing this expression by n, so n divided by n is 1, and 1 divided by n is 1 over n, so that's that. Minus 5, and we're doing the same thing with n cubed, right? We're going to think of it as n times n times n. We're going to divide this by n, giving us 1. We're going to divide this expression by n, giving us 1 plus 1 over n, and this expression by n, giving us 2 plus 1 over n, and then on the bottom, we've just got the 6. Now, if you think back to the example we did the other day, we had like a plus 5 over n or plus 7 over n, right? And that sum is just going to be that number, right? So if you have like a plus 5 over n here, when you do the sum, it just becomes 7 or whatever the number was, right? You do the sum of I equals, if you add up n of them, right, where, so if it was the sum as I equals 1 to 10 of 7 over n, it would be 7 over 10 plus 7 over 10 plus 7, right? So it would be 7. So it's just that constant. Okay, 25. Now, let's do the limit, right? So as n approaches infinity, so we no longer have an n on the bottom, right? We're not dividing by anything we shouldn't be. Okay, so 25, and what do we got? 3 times 1 plus, times 1 plus 0, right? So as n approaches infinity, 1 over n, over 2 minus 5 times 1 times 1 plus 0 times 2 plus 0, 2 plus 0 over 6. And that's 25 times. Okay, so we've got 3 times 1, which is 3 over 2. minus 5 times 1 times 1 times 2, which is 10 over 6, right? 10 over 6. You know what? I'm going to leave it as 10 over 6. Because to add these, I need a common denominator, and if I change that to 5/3, I'm going to have to change them both to sixths anyways, right? So might as well just leave that with a 6. So we'll make that a 6. So it's 25 times 9/6 minus 10/6, which is negative 25 over 6. Okay, so we have used the definition of integrals, which we studied in the previous unit, right? The sum of n rectangles. To evaluate the sum from 0 to 5 of 3x minus x squared dx, and we get negative 25 over 6. Right, now you're going, but wait, negative, and so the rest of this is going to be, okay, so really what are we finding here? What's going on here? So sketch the graph y equals 3x minus x squared, labeling all intercepts, shading the area bounded by, and the x-axis, and the vertical lines x equals 0, x equals 5. All right, how do we find the intercepts? So we set this equal to 0, right? The intercepts are when y equals 0, right? X-intercept occurs when y is 0. We factor. And we say, well, we got one intercept here, and we got another intercept here. So we get an intercept at 0 and an intercept at 3. If I'm going to sketch this thing out, what do we want? Okay, so 0. So, all right, it's a quadratic. It opens down, right, negative x squared. So it goes through 0, 0. Actually, let me extend that. Actually, let me redraw that. Okay, so we got 0, we got 3, we got 0. We need 5 as well, right? So 5. Draw that. All right, and we want the area, we want to shade in the area bounded by this curve, the x-axis, and the vertical lines x equals 0 and x equals 5. So let's shade. So we've got this area here. And we've got this area here. Okay, so let's call this area 1, and call this area 2. So we have these two separate areas. Okay, so in part C, which is on the back of the page, we're going to use antiderivatives to determine the shaded area above the x-axis, right? Which means we need to go from 0 to 3. That's what's above the x-axis. Okay. Oh, wait, what? Did I go too far? Oh, here, sorry. On the same page. Use antiderivatives to determine the shaded area that's above the x-axis. So we want to go from 0 to 3. So we're going to work out area 1, right? So for area 1, f of x is going to be equal to 3x minus x squared. That's the upper function, right? And the lower function is 0, right? Just y equals 0. So it's just 3x minus x squared. Capital F of x is equal to what? No, let's go with squared.
Sorry.
minus, use the anti-power rule, which x cubed over 3, yeah. Okay. Plus some constant, right, which we are going to conveniently ignore when we do this, right? So the area we want, area 1, which will be A of 3, will be f of 3 minus f of 0, which is, so 3 halves, 3 squared, minus 3 cubed over 3 minus 0. Minus 0. Just to be thorough. Wait, let's be more specific then, just so you don't see that. So 3 halves 0 squared minus 0 cubed over 3.
Do you have to do anything with the C?
No. It's gonna, I mean, it's the same for f of 3 as it is for f of 0, right? That's why we can, in essence, sort of ignore it. Because, yeah, it's going to be part of f of 3, but then you're subtracting f of 0, and it's also part of f of 0, so it's just going to subtract off. So we don't bother. And what do we got? 3 is 9, 27 over 2. And 27 over 3, which is 9. So that's 27 halves minus 18 halves, or 9 halves. So area 1 is 9 over 2. 9 halves, 4 and a half, whatever. Use antiderivatives to determine the shaded area below the x-axis. So now we want area 2, right? So we're going to go from 3 to 5. So area 2. So for area 2, what do we got? G of x is equal to, so the upper function is 0, right? So we're going from y equals 0 down. So it's 0 minus 3x minus x squared, which is equal to negative 3x plus x squared. All right, and so what's capital G of x? An area between two curves. This is your upper curve. This is upper function, lower function. Right, so it's upper minus lower. What? Plus 1/3 x cubed, right? X cubed over 3. So we want area 2, which is a of 5. So that's going to be g5 minus g3. So negative 3, 5 squared over 2 plus 5 cubed over 3 minus, always parentheses here, right? Means if we don't want it to be lonely, then let's put parentheses around both. Not needed here, but just sort of handy to say, hey, look, here's g of 5 minus, and I'm doing g of 3. So minus 3 squared over 2 plus 3 cubed over 3. All right, so we get 25, negative 75 over 2 plus 125 over 3. All right, what do we get here? Negative 27 over 2, we're going minus negative 27 over 2, so that's going to be plus 27 over 2. And we got 9, right? 27 over 3. So minus 9. All right, common denominator is going to be a 6. We're going to have to multiply this by 3, negative 225. Multiply this by 2, plus 250. Multiply this by 3, 81. Multiply this by 6, 54. Right? So we've got a common denominator of 6 now. We've changed all the numerators to be the same, right? So you take any one by itself, that's negative 75 over 2, that's 125 over 3, and so on. Okay, what do we got? 25 plus 81 is 106, minus 50 would be 56, divided by, what do we got, 52? Yeah, 52 over 6,
26 over 3.
which is 26 over 3. All right, so what does negative 25 over 6 have to do with 9 over 2 and 26 over 3? All right, so what do we got? So from part A, we get negative 25 over 6. Part C was 9 over 2. And part D was 26 over 3. Well, if I'm looking for a relationship, let's call this, let's get everything with a 6, right? It'd be a little bit easier to work with if we have this as 27 over 6 and this as 52 over 6. So what's negative 25 over 6 equal to? I think this, right? And what was this? Area above? And this was area below? Okay. All of which will be nicely summarized in the box at the top of the next page, which says, in general, if a function takes on both positive and negative values, then we can interpret the integral from a to b of f of x dx as a difference of areas, a1 minus a2, where we have the area of the region below the graph of f and above the x-axis, so the positive region, right, in essence, and the area below, which will come out as the negative region. And that's the last thing. So evaluate negative 1 to 2, the integral from negative 1 to 2 of x cubed dx, and interpret the value as a difference of areas. Use a diagram to illustrate your interpretation. Should we draw a diagram first? Or, we could. So it's an x cubed. And we're going from negative 1 to 2. So if that's negative 1, we've got this. And 2, we've got this. So do we expect to end up with a positive or a negative answer? Positive answer, right? We've got a greater area above than we do an area below. Okay, so what do we do with this? Come down here. Equals. Here's how we write this. Okay. So we take the derivative, the antiderivative, right? X cubed. So that's 1/4 x to the 4th plus c, and the notation is like this. So we say we're going to evaluate this from negative 1 to 2. Or from 2 to negative 1, I guess, really. From 2 to negative 1. So we're going to substitute in, for x, a value of 2 into this. Okay, we got plus c. And from that, we are going to subtract the lower value. Okay, plus c again. Now, really, you don't need the c's, right? Because you got a plus c minus, again, the plus c, so it doesn't really matter what those constants were. So what do we got? 2 to the 4th is 16 divided by 4 is 4. Negative 1 to the 4th is 1 times a quarter is 1/4, so 4 minus 1/4. So that's 3 3/4 or 15 quarters. So what's the value as a difference of areas? The difference between the area above the x-axis and below y equals x cubed, and the area below the y-axis and above y equals x cubed is 15 over 4. Okay, so that's basically what this means. The differences, or the difference between the area above the x-axis and below y equals x cubed, and the area below the x-axis and above y equals x cubed is 15 over 4. Now, what would we do? If we wanted the total area, then we would have to split this up, right, and work out two separate areas, from -1 to 0 and from 0 to 2, right? So we need to say, well, where are you crossing the axis? So the total area would be the absolute value of, right? That way if it's below and it's negative, that's fine. We're going to take the absolute value of the area from -1 to 0 plus the area from 0 to, where are we going? To 2. And the absolute value of that area as well. Okay, so if you split it up and do one where it's the area below and one where the area is above, take their absolute values, add those together, you'll get the total area. And that's it.